Hey everybody, and welcome to another JASP tutorial. In this tutorial, and it's been a while since I've done an episode of the tutorial, but I've been asked to do multiple regression. So one of the more recent episodes of this series, I did a bivariate linear regression. Well, for this particular episode, I'm going to go ahead and do a multiple linear regression, so that is more than one independent variable or more than one predictor variable predicting one outcome variable or y variable. To get us started, I want to go ahead and let you all know that I am using the latest JASP release, which is JASP 0.11.1. This came out in October of 2019, and so it is their latest one. And we're going to go up here to regression. You click on this regression button, and you go to multiple regression. But to get us started, I'm going to go ahead and just open up a data file from the JASP data library, and I will come right back to it. Okay, so here we are with the album sales data file. If you go to the hamburger button over here for the menu and you open up the open and data library, it's the second one down for regression, categories number 4 regression. So that's where I got it from, just in case you were wondering. I wanted to go ahead and use a rich data set that isn't really too confusing, and we have a description of the variables that you can read here. You can go ahead and pause it here. This is from Field's manual discovering statistics using SPSS. So this was transferred in from there. It was ported in there. So you can see here that the linear regression already exists here. And I've removed a couple of other analyses that comes with this particular data library file because I just want to show you the multiple regression part of it. You can look at the other videos for how to do descriptive statistics and things like that, things of that nature. So we're just going to jump right into the regression. And as I said at the top of the video, you click on regression, and for the frequentists, which is the one that I'm doing here, you click on linear regression, and it's the same menu of options for a bivariate regression, that is one x variable, one y variable, and a multiple linear regression, which is multiple x variables, more than one, two or more, and then one y variable. It's the same grouping of options under here in linear regression. So I'm going to go ahead and hit the arrow there, the triangle, to bring this down. And when I do, you'll see that I've already, or the file already places the variables where they need to go. And so if we go back up here, we are trying to predict album sales. So sales is in the dependent variable slot, and then because it's a multiple regression, we want to go ahead and put all of the other variables, which is the amount of advertisements in thousands of pounds, British money, and airplay, how many times the song was played on radio stations, and then attract, which is an ordinal variable, how attractive people found the band's image from 1 to 10. Okay, so these three variables are entered in the covariates box, which is where all of your x variables will go. And one of the things that I didn't mention in my previous video is this method, how these variables, these covariates, are entered in to the model. So when you do a bivariate regression, you leave this as enter because you're only doing one model. But let's say you want to do some sort of stepwise or hierarchical linear model, and so you want to go to method here and choose which one. Now, if you're going to do a simultaneous regression, you leave it as enter. It basically puts all of these into the same model and regresses it on this dependent variable. So The other methods that we can do, though, is we can do other entering. So for this, for backward and forward, you would go in an order. So forward would go, 1, 2, 3. Backward would go 3, 2, 1. And for backward and forward, there's further criteria that you would set, and I'll show you those options in a little bit when we get to the options. So, based on the values of some of the statistics that are revealed in a regression, you can enter in variables back and forth by using backward and forward. Now, you would use these in a stepwise way if you have the theory supporting going backward and forward. We want to prevent, QRPs, questionable research practices, by using these. You would have to indicate a theoretical reason for doing stepwise in a forward or backward direction, and which is adding and removing based on some criteria like p-values. The third one here, or fourth one I should say, is stepwise. This is essentially going in order, a model adding in these variables in order. As far as I'm aware, JASP does not do this like SPSS or another feature-rich program. I mean, I don't mind how it does it, but if you have a lot of variables in here, and the regression assumptions aside, you really shouldn't have a ton. And getting all of these models entering one at a time to you should have a theoretical reason for entering in a new variable to see what happens to r squared, and that's fine. But as far as I'm aware, stepwise doesn't work in the same way SPSS does it. And I do have a request on the GitHub page for this, and it recently got bumped by somebody else asking for a true stepwise function. And so, unfortunately, I'm not going to show that in this one. I'm going to do it a little differently. I'm going to be able to get two models just to show you what happens with the r squared change. But for now, I'm going to go ahead and put in just the enter method. And so it's going to put all three of them into a single model. And if we crack open the model menu here, you can see that I have my model terms. Here are my components, and you can bring them back and forth if you want to. And you see here this checkbox, add to null model. So this is the model 0 that JASP is going to create. And you can see here model 0 on the output, because I've put all three of them in there. And you can see that the null model includes adverts, airplay, and the attracts variables. Okay, so adverts, airplay, and attract. And what this is telling you is the basic model statistics with having all three in the model at the same time. But before we go over the output, I want to finish with the options here. So we have model. I'm going to go ahead and collapse that. Moving on to statistics, you would choose estimates here. You can bootstrap if you want, which is great. Bootstrapping. You can put however many bootstraps you want. 5,000 is typically what you'll see when people report bootstrapping, and so that's the default value in there. You can get confidence intervals for your coefficients, which is, generally speaking, a good thing to do. You can grab a covariance matrix. I'm going to go ahead and throw that in. You can get your model fit, which is a great set of information that if I uncheck that, you will see that I don't have the model fit on there. The r squared change. Now, if you are doing a enter method with all of them in at one time, you won't need R squared change. And so I'm going to leave it off for now until we, look at doing it in a more stepwise fashion. Okay, so leave it off for now. Descriptives, these are your means and standard deviations. You can partial correlations, which are useful if you need to make estimates of and explain relationships between one variable and another. It's better to have that than just zero order correlations. And so this will give you all three. If you check this box, you'll have your zero order, your part, and your partial correlations for whatever relationships you want to talk about while not including other variables in the variance. And then we can have collinearity diagnosis to let us know whether or not we violated assumptions. So that's important. Alrighty. So you can also get statistics for your residuals. And we can click on statistics here, which will give us where is it here? Our residual statistics. So what the predicted values are, mean, standard deviations, all of that, and you can see it'll plot this for us. We also have case-wise diagnostics here, which will give us our standard residuals for each of our cases. There are 200 cases in here, and so it skips a number of them as they change values here. Case-wise diagnostics. There are 12 cases that exceed the standard residual of 2, and so they are kicked out. And so this is a good way to check your data by using case-wise diagnostics if they violate some residuals assumptions that you want to use. Alrighty, now collapsing that, so these are all of the statistics we would use in like a paper or something. The stepping methods criteria. Now, again, I'm going to back up here to forward and backward, as well as stepwise. This is where you would change the criteria for R squared value changes and whether or not it should be in the equation or not. And you can use the p-value. And so in order for a predictor to enter the model would have to be less than 0.05, and it gets removed from the model once it hits a p-value of 0.1, or you can use f-values if you know what those are. And here you would have the constant in the equation. Let me go up to the coefficients, and so that would be your intercept there. And if I uncheck that, the intercept disappears, but we don't want that because there's always a good reason for the y-intercept. And then your Vopk-Selke maximum p ratio, as in all of my videos, I ignore that one. So, and the final one is plots. So you could get a bunch of plots here. You can get your residuals versus your dependence, your residuals versus any of the covariates, residuals versus predicted values, residuals versus your histograms, and I believe some of these are on here already. Yeah, so here is the residuals versus predicted as checked. Like I mentioned with the residual stats, they go together. You can have the histogram for the residuals. You can see that the mean is just about 0. And then you can get the QQ plot, which will plot the theoretical quantiles versus the standard residuals on a nice number line here. And you want to get it as close as possible. That's nice. And then you can also have partial plots. Okay, so let's go through these statistics here and what you're looking for in this full set, this enter method where I put all the covariates into the model. So we have our only model here, zero model, our null model. Okay. Ignore the writing here because this is when there are two. This is when there will be two models. I'll show you that in just a second. But let's look at the full enter simultaneous regression with all three predictors. We have an R of 0.815 and an R squared of 0.665. An adjusted R-square for biasing, 0.66, so generally speaking, it's about the same. And then a root mean square error, RMSE, of 47.09. So this is not a bad model. This is not a bad model. R is pretty good, R-squared's really good, and if we go down to the ANOVA, which is predicting whether or not R-squared is really good, we see that we have a huge F value with our ANOVA table, and then, of course, the p-value then with a huge F is going to be less than 0.001. So, further evidence that this R-squared is a great fit with all three predictors. But you'll see when I break this out what changes when adverts is all by itself. And going down here to the coefficients, so these are your unstandardized coefficients. So these are your B's. Either capital or lowercase b is what I see frequently. So these are your slopes for each of these predictors. And so they're expressed in the units of y over x. So how many sales versus adverts, how many sales versus airtime plays, how many sales versus the attractive rating. So for every increase in y, for increase of x, that sort of thing. And the unstandardized coefficient has a standard error because it's a measurement. So there is always going to be error associated with the measurements that we take for any given sample. Now, these are your betas. The standardized column, this is your betas, so Greek letter beta. These are standardizing them on a scale from 0 to 1 so we can compare them directly. Because these unstandardized coefficients are generally speaking in the units of y over x, we can't really compare them directly, and this is a great example of being able to compare them directly, or not being able to compare them directly, actually, because we have a scale of 0.085 versus 3.3, 7, and 11.1, whatever. Obviously, attract is huge compared to the other two. 11 versus 3 versus a very, very small number, less than 1. But that's not the whole story, because the scale of attract is much different from the scale of airplay and adverts. And so we want to standardize those coefficients so we can compare them directly. And we see that actually attract doesn't really do much to the equation. It doesn't contribute a ton of variance to the model. Not to say that 0.19 isn't a significant predictor, because as we can see here, they're all significant predictors. The intercept is not. For some reason, there is no 95% confidence interval, and this seems to be a bug right here. 9,500% confidence interval. No wonder there's no ability for that. And then here are your collinearity statistics, so tolerance and VIF will tell you whether or not these coefficients are violating anything. And then here we have the descriptive stats, so 200 of n for each of these: mean, standard deviation, standard error, that sort of thing. Here are your part and partial correlations. And then here's the covariance matrix, coefficients covariance matrix, and so I have all three in there. And of course, it's only the top above the diagonal there. Here are your collinearity diagnostics, so dimensions, the eigenvalues for this. So it looks like dimension 1 is the only one with a good eigenvalue. Everything else is significantly less than 1 there. And then we have our variance proportions. And you can see here from what the collinearity diagnostics are for. Okay. And then again, case-wise diagnostics, residuals, and plots. Residuals seem to have a nice normal distribution. QQ plot, nice model fit, because they are super nice and super normal. So that's what that looks like in what a full simultaneous regression looks like. So let me go ahead and do a couple of changes here. Let me go back to model, and I'm going to uncheck airplay and attract. So it's going to actually give me two models now. Okay, so adverts will be the only one in the null model now. So adverts and sales. And then model 1 is going to have all three. And so I kind of have a poor man's stepwise hierarchical, truly block stepwise. Which, if you look at the help menu and you go down to the method and you look at the method specifying, they do have a note. The JASP developers have a note that says, note that the present release does not allow for more than one block. So to get a truly hierarchical multiple linear regression, you need that ability for multiple blocks. So backward, forward, and stepwise really aren't going to give you that full control over the blocks. But this is a backwards way. There's a backwards way to do it. And so we can at least just put adverts in there. So hey, how good is advertising in predicting the sales of a record? Before we even talk about airplay and the attractiveness of the advertisements. And so here you get the two models, 0 and 1. So model 0 is the null one. This is only adverts, as indicated by the note. Model 1 includes the other two, airplay and attract. And you can see here, if I add in the r-squared change, didn't click. There we go. As I add in the r-squared change, now the notes are going to match up better because we have r-squared change here. You're going to see that model 0, now it's only adverts. So, of course, those things are going to change. Model 1 looks exactly like what we just did. And here we have the r is 0.58 and r-squared is 0.34 or thereabouts. But we're going to add in the r-squared change here. So r-squared change for the first model is the exact same information that you get from the ANOVA table. So there's really nothing in there that is going to give you any information. But what you want to look at for the r-squared change is what happens now to r-squared on the second model. So model 1 here, we end up with that 0.82 and then the 0.67, and you can see that r-squared change is 0.33 increase because it's a positive number. This could be positive or negative. It's a positive number. 0.33 added to this value here, and you get that value, and then you have an additional amount of f and about the same df, but of course the denominator df goes down because I've added in a couple more predictors. df1 changes slightly as well. And so you end up with an f-square change, and you can see those changes down here, 99 and then 129.50. Now, this f is just assessing this r-squared, so that's why it's smaller than over here. But obviously you can see, I wish I could highlight it. Obviously you can see on this line here, it's the exact same thing here. This f and df and p are assessing 0.33. This one over here, this 196, and then f of 129.50, p is less than 0.01, is this r-squared, the 0.665. That's why you get the dramatic difference here. So that's why this line here looks just like this one down here. But when we add in this new r-squared, because now r-squared is 0.665, we need to see whether or not that change has value, is statistically significant, is valuable and meaningful for my argument that it's not just advertisements, it's the quality of the advertisements, how attractive they are, and how much airplay that leads to album sales. So you need to have good advertisements, you need to get airplay on radio stations. It's not just the number of advertisements, it's more than that. And so that's the argument you would be making from these, just these two in particular. You would say, oh, yeah, that's exactly right. That is so much better to add those two variables in to predict better album sales. We get a better prediction. And in the coefficients table, the model here just has the intercept and adverts. I mean, adverts is perfectly fine predicting album sales. There's a positive relationship there, almost 0.6 in the beta. And then if we add in airplay and attract, you'll see that again, these are the same coefficients from earlier in the video. And then again, nothing else really changes except for the part and partial correlations. When we change this, you can see the part and partial correlations are the exact same as beta because it's the only predictor in the model. But then when we add in airplay and attract, those part and partial correlations change. Okay, and then same thing with the coefficients covariance matrix. There's no covariance matrix for the bivariate regression, but then we add in the other ones and we end up with the covariance matrix, which does mimic the simultaneous regression that we just did. Same thing with the collinearity diagnostics, and nothing else here changes. So that was a super quick, but also not super quick, because this video is almost 30 minutes long, linear regression overview. I know I didn't get to everything. I know we could go through it even more, but I thought this would be a good way to compare a simultaneous multiple regression with a two-block poor man's two-block using the null versus non-null modeling in JASP. Please leave your feedback, questions, and comments down below. Thank you for watching another JASP tutorial. Bye.